Our project is an integrated digital dashboard steering wheel for a go-kart. Real-time data from the go-kart is displayed on a touchscreen LED display mounted to the steering wheel, so that the driver is able to optimize their driving and improve lap times. An accelerometer, tachometer, and infrared sensor are mounted about the go-kart to take data on the acceleration, velocity, engine RPM, and tire temperature of the car. Our inspiration for this project was Formula One. Noah, Nick, Adam, and I, all fans of Formula One, and after the new cars were released for this coming season, we've all been following the engineering design of them intensely. A major part of F1 is the telemetry data that's supplied to the support team and the screen on the steering wheel, so that both the driver and the support team can help improve the racing and reach higher positions and maybe win. It was this steering wheel that inspired us to develop this project.
The Telemetry dashboard operates in the integration of 3 sensor subsystems that record important information regarding the tire temperature, the engine's revolutions per minute, the velocity, and the acceleration of the go-kart. The first of these sensor subsystems is the accelerometer, which when moved along the X, Y, or Z axes outputs a vector component for the acceleration. Furthermore, because velocity is the integral of acceleration, via Arduino logic, the accelerometer's analog serial data is able to be converted to the go-kart's current velocity. Furthermore, the tire temperature sensor subsystem operates such that an infrared temperature sensor is placed in front of the left rear tire to record the amount of infrared energy generated by the tire when rotated. Because infrared energy is proportional to the temperature, the 4 pins of the IR sensor, which are soldered to one braided wire, are connected to 4 distinct analog input pins on the Arduino to stream the tire's temperature in units of Fahrenheit via Arduino logic. Lastly, the tachometer sensor subsystem operates such that a wire is coiled around the go-kart spark plug to generate a current in the wire. These current pulses are sent through an inverted monostable multi-vibrator circuit, which consists of a 555 timer integrated circuit.
When we think about the Arduino code for the system, the accelerometer code is actually quite straightforward. After we were able to understand what the sensor was reading 1G as, using sort of the Z-axis of the accelerometer, we could then sort of do some simple mathematics to get back to the G measurement in all axes. Then for velocity, we would simply store a certain set of values from the accelerometer over a certain period of time, add those values together, divide by time, and then get velocity. It's a very simple way of numerically integrating. For the temperature sensor, we relied a lot on the library, and again, it was a very straightforward implementation. The tachometer, however, was a little bit more complicated because we needed to basically detect the rising edge we were getting from our input signal and then measure the time from a pulse to the next pulse. And then from there, we could work back to revolutions per minute.
Now, there were a few issues that we ran into in the development of our dashboard display. For one, originally our design had also included a sensor that would monitor the level of the fuel currently in the tank. Now, this sensor would have operated using a floating device attached to the side of the fuel tank, and as the fuel level would rise, the float would rise, hence the resistance values as picked up by the sensor would change, allowing us to monitor precisely the level of fuel. Now, we had some issues with this. For one, drilling into the side of a gas tank is actually a really bad and dangerous idea without the proper equipment and tools. But never mind that, the design of the fuel tank itself is safety oriented. At the top, there's a lip that comes down into the tank. This way you're not splashing yourself if you're filling up fuel, but this also means that any device that we would have had would not have been able to use its full range of flotation motion in order to measure the level of the fuel tank. And for this reason, we had to scrap this part of the design. Another issue we ran into was with demugging the tachometer. Now, for the longest time, we were not able to successfully capture the readings of the tachometer. Anything that we would measure, we could see in our Arduino code. However, this would not match up with the revolutions per minute that we were measuring from the Arduino, and we were able to verify that we were wrong because we actually have footage of the engine spinning in a slow-mo as seen here. Now, with extensive testing and modification to our circuit design, we ended up eventually being able to resolve this issue by switching our circuit design and